All right, well, it's 11 o'clock. So as people continue to filter in, I think we should go ahead and get started. So welcome everyone. I hope you had a great summer and welcome to the this latest season of the CGD seminar. We have a great lineup of speakers so far. And I would encourage everyone to keep the great suggestions coming for people that we'd like to see present this fall and this year. I'd like to start off by reminding everyone of our code of conduct in CGD. These are just, sort of collective values that we share in discussing and presenting some of this work. So to offer constructive feedback, to share the air and make sure all the voices are heard, to acknowledge teamwork, encourage innovation, show appreciation for work, and to consider all the new ideas that we're hoping to see and encounter this year. So with that, I would also say to please, as the talks are going on, to keep questions until the end, except for any clarifying questions that might come up, and feel free to put those in the chat as well. So for our first speaker, it is my pleasure to introduce Peter Webster. Peter is Professor of Earth and Atmospheric Sciences at the Georgia Institute of Technology. He received his bachelor's from the Royal Melbourne Institute of Technology and PhD from MIT. Prior to his current position, he served as faculty at several institutions, including as director of the Atmospheric and Ocean Sciences Department at CU. He's a fellow of the AGU, AMS, and AAAS, and has received numerous awards from his organizations, including in 2015, the International Award in recognition of using science for the benefit of society in developing nations. So today he'll be speaking about inter-hemispheric synchronization of climate. So Peter, feel free to share your screen and take it away.
Sure. Let me see. Okay. Stop my video. Can you see my screen?
Yes, we can.
Okay, yeah.
It's not in the presenter mode.
Oh,
yep, there it is.
Can you see now? Okay. Well, this is interesting. Looking back over my life and how long I've taken to thinking about this problem off and on. And I'm not going to tell you the year, but it was 1972 when I started thinking about this. And that's just a couple of years ago. So it's a problem. How can I put it? Is oops, hang on. I've lost my. I can't see my own screen.
I think we can't either. Maybe try sharing again.
Yeah, I've got to dig it up again. Okay. Sorry about this. No.
So Peter, it's Tracy. So at the bottom where it says share screen, is it not letting you do anything?
Well, just 1 minute, so I'm
Sure.
not sure I've got the right presentation. About 10 versions of this. So let me try share screen. Here we go. So share, okay. How is that?
Well, we're seeing all of your screens.
Oh dear. Okay. Don't want that. So let me. Let's see. I hope this is the right one. Just 1 second.
Mhm.
In presentation mode. Here we are. Okay.
There you go.
Okay. Yeah.
Perfect.
Well, this is a. What you're seeing here, by the way, is the 370K isotropic field and showing potential vorticity. And you see it's very wavy. And I'm going to argue that there's a lot of organization within that, but just beautiful breaking waves, like you see up here. Oops, end of that. 1 second, I'm sorry. Yeah. We're going to see all types of organization here. Maybe we could put some type of sense to it. We're going to suggest there are a lot of peculiar structures in climate. And one of the oldest is the interaction of tropics and the exotropics in both hemispheres, something that we think that we understand, but I would argue that it's been a long time, again, 60 years of people working, not me this time, who are not quite sure what it means, or is it organization with it? And a lot of interhemispheric dynamics goes through ducts and cloud bands, and can we tie all those into some type of structure? And work by Graham Stevens some time ago showed that there's interhemispheric symmetry of top of the atmosphere radiation. And also there's a peculiar interhemispheric symmetry between hemispheres of annual precipitation. And then we have these way out things, the synchronicity of ice age timing and the rapid growth of global dust storms on Mars. As you think when you came today, you hear me talking about Mars. But anyhow, this is a little bit of it. And I'm going to argue that there are two ways of thinking about this. One is in a reductionist manner, where you pick a certain thing like monsoon rainfall and you study that. Or you might think about monsoon rainfall relative to breaking waves in the Atlantic, the Pacific. And then you can tie those together, and bit by bit, you have a holistic system. I'm going to argue that the overriding constraint that we find ourselves dynamically is the conservation of isotropic potential vorticity substance. This is the Haynes-McIntyre impermeability theorem, which is becoming quite known, but probably will become a lot more. We'll get there. So the issue of tropical-extratropical interaction, nobody really cared about it until the 1950s and 60s, when numerical weather prediction became a reality. And there's a need for dynamic description of the tropics. Now, some of the earliest observations by truly marvelous scientists, by Herbert Real, he suggested a strong connection between extratropics and tropics. And these observations are very difficult to explain in terms of like this thing here on the right, a prevailing zonally symmetric Hadley circulation. So what we're going to find is that there are joint dynamics between extratropical-tropical interaction and the reverse, extratropical-tropical. And these are governed by simple constraints. Now, first thing, let me talk about the first peculiarity that Graham first brought out 10 years ago. When you look at the two hemispheres, and there are pictures there, surface albedo, planetary albedo, contribution to the ground, and so on, they're vastly different. And it's almost impossible a priori to say, oh my goodness, they're the same. How could it be the same when almost all of the northern hemisphere is land and all of the southern hemisphere is ocean? And so what he found was that when you look at the top of the atmosphere, the net radiation at the top of the atmosphere averaged over each hemisphere was about the same. And you can also say that the albedo is almost the same too, and all within about 2%. So this is a remarkable finding, and we've struggled to understand that. So what are the consequences of this symmetry? You look at the top left-hand corner here. This is the OLR, the black curve. This is only average. And this is the net solar radiation in, which gives you the annual average top of the atmosphere heating here. And when you look at these numbers, my goodness, the heating and cooling, these two add up to that. But the surprising thing is that the interhemispheric versions of these things, given the enormous difference in cloud type, surface, ocean, atmosphere, they're the same. So how can this be? So increases in cloud reflection and height induced by changes in circulation, but what controls the circulation? And the other thing too that we need to think about is that when you look at the model differences, they're in the bottom here, surface and atmosphere, or the top of the atmosphere here. These are the northern hemisphere minus southern hemisphere, annually averaged top of the atmosphere. And you find they go from 0 to 6 watts per square meter. You think, oh, so what? But when you think you're running a climate model that may have an error of 6 watts per square meter, which is about the order of the expected downwelling radiation at the surface, one needs to be a little worried. So one at least needs to know how well a model is doing. So this is actually a very, very good test for how well a model is doing. So it gets stranger when you look at the relationship of precipitation between the hemispheres. And look at this beautiful chart here, put together as a precipitation rate by NASA. And you couldn't get anything different. Again, you have land and ocean bands, and on it goes. There's no way that there should be a similarity between what happens in the northern hemisphere and what happens in the southern hemisphere. So when you compute the annual average per hemisphere, you get quite a surprise. And this is the precipitation rate by region. This is total 13.56, and it's divided into ocean and land. So the global majority is ocean, and land is 3.1 versus 10.5. And as you go through per season, you find that the total precipitation rate, actually the same as volume, by the way, the volume rate is almost identical between the seasons. Then when you break that down to southern hemisphere and northern hemisphere, you find 6.88 versus 6.68. And of course, difference versus land and ocean. So all of a sudden, this amazing annual similarity in precipitation, despite a diagram like this, which shows you should expect something completely different. And you look down at the bottom here, and you look at the land precipitation, the ocean precipitation, and the total, and you can see very, very similar, within 2%. This is work, by the way, with colleagues of mine, Vila Tomer and Carlos Oyas. We hope to finish this in 2021. But there's a problem I'll mention right at the end, why it might be 2022. I'm optimistic. Also, when you look at the ocean and land precipitation between 40 degrees north and 40 degrees south, this is very peculiar. You find that the ocean, which is red, and the land, which is blue, they tend to compensate about around 0. So the net variation is 0 over a long period of time. In other words, there's a compensation between land and the ocean, but it adds up to that 0 difference I mentioned before. And if I were to look at the NCEP reanalysis plot from all the net ocean heating, which is in black, and the net ocean, land heating, which is in red, what I find is that there's a negative correlation of 0.82. This is detrended. So something strange is going on in the atmosphere. It gets even more strange when you look at the, for example, it doesn't matter, the ECWF reanalysis, and you correlate the summed rainfall over land with precipitation everywhere. And what you find are these great compensations when the land is wet, the ocean is dry. When the ocean is wet, the land is dry. This, of course, is the 0.82. But you might say, oh, this is nothing more than ENSO. But is it, or is it something else? Or is it, if it is so, what's controlling this symmetry of precipitation? Just to show you, this is the long-term PCM 20th century run, GFDL 20th century run, and you find the same thing. Oops, oh, if you're quick enough. And what you find is a negative correlation. This is land and sea of 0.63 or 0.74. In other words, significant variations. But no, just this is a curiosity, and I thought about this. Oh my God, my very first job. I was a consultant at JPL, and they were wanting to know when they landed the Mariner spacecraft here on the equator, how strong the winds will be. And they were worried about dust storms. So I thought, oh, that's interesting. And they occur irregularly, although there's some correlation with the solar cycle where they are in their orbit. But what happens, this is May 28th, this is July 1st, it's gone from small dust storm to a global dust storm. So I've searched the literature for reasons for this, but Mars is a rotating stratified atmosphere, the same as Earth. So if there are global synergies, would they also apply? You would expect them to apply to a dynamically similar planet such as Mars. So we'll look into that very briefly. Sorry. And then there's, just close the door, hang on. So sorry, when you give a talk from home, you have lots of dogs around. So I apologize. There's also this question of paleosynchronicity. And while the orbital forcing from Milankovitch cyclones is anti-symmetric, in other words, you know, reduce northern hemisphere winter insolation, increase summer, the response is often a global ice age. And there have been lots of questions about why this is the case. So what produces the synchronous response? Is there an explanation? Is there any one? Is it teleconnection between the northern hemisphere and the southern hemisphere? As the northern hemisphere cools, what happens? Weber has written a nice paper a few years ago on that. Just this is the exposed land in the Australian sector. This is from a paper a long time ago when we were trying to understand the migrations of indigenes during the ice ages. That's very interesting. And during that time, this is the extent of the Antarctic ice sheet, which is considerably larger, about 25% larger. So we were interested in trying to understand that. I'll come back to that. So I'm going to talk a little bit about how one thinks about this. And there are two ways you can tackle problems, and one is a scientific reductionism where you, this little chap here, by the way, my parents, when I was, this is me, bought me this beautiful little horse and expected me to push it around or ride it. All I did was put it on its side and spin the wheels. And so I consider myself an early reductionist, trying to work out how the wheels work. So what you can do, it's a scientific reductionism. It's essentially Descartes is an approach where understanding the nature of complex things, reducing them to the simple parts. And there was this thing called the Vaucanson duck, was it mechanical duck, where all the bits and pieces, it ate food and it defecated, not to be crude. So you can do the same with the Earth's climate and just break things down very, very simply and just consider one little part. Oh, the Indian monsoon, very important. But should you consider the whole to be able to talk about the Indian monsoon rainfall? And this brings into scientific holism. It's the idea where you view something as a whole, not a collection of parts. Now, there's something nice and tractable about reductionism, in the sense that it is a simple way of looking at things, but the results often aren't complete. I won't have time today to talk about Hofstadter and his idea of complexity, where he points very, very strongly to holism, but sometime maybe I'll talk about that. Oops. Okay, so in the tropics, 1945 to 1950, and this is a map of this is 1945, my goodness, not many observations. This is a map of the 1,000-foot streamlines, and Herbert Real was involved in training pilots for with war effort, and he found a number of things, and that the trade winds were extremely steady. You can see this is a cross section here, XY plot here, so very, very steady things. But you notice in the upper troposphere, there were all types of eddies moving through, and you can see them here. This is a time section, and this is just extratropical waves moving through. So he was greatly surprised. Intermittent appearance of high tropospheric westerlies on the equator is a foreign thought. Remember, people were thinking Hadley circulation at this stage. Yet they do occur. Since the high levels is so steady, coupling to high latitudes between the circulation and northern southern promise to find an important link in understanding the circulation. And so what he said was an intrusion of extratropical type disturbance into the heart of the tropics. So this is a remarkable observation. This is now, oh my goodness, 80 years ago, isn't it? But early attempts were piecemeal and reductionist. Most models in theory assume zonal symmetry and propagating disturbances occupying the entire tropical. So it was a great problem. And then China came along with scaling arguments, which suggested that it was almost impossible to get disturbances in the tropics from in situ purposes. And that was again assuming zonal symmetry, but to be fair, they didn't have charts like this. This is an OLR and isotropic chart. So it can't be too critical. But his argument was that the atmosphere was either barotropic or baroclinic, and in the extratropics, your favored scale of motion was 10 to the 6 meters. In the tropics, to get divergence, you had to have 10 to the 7. It should be +7, not 10 to the -7, not that small. So he came up with an interesting surmise. Well, it's more or less said that as you can't have in situ production of waves, then they must be forced from outside. So the position of the ITCZ, which wasn't done locally, produced locally, it was due to large-scale external forcing. So a lot of studies, my friend John Young looked at a zonally symmetric structure and had a wave source. And I won't bother you with this, except to say there were two major results. Only the longest, wave number 1 and 2, would make it to the equator. But observationally, they had no energy. So all of the wave energy was absorbed near the U=0 line. So there's no way of explaining Real's beautiful observations. Mankin Mack came along and introduced vertical shear. And he also found there's a certain history to this. John Young and Mankin Mack were students at MIT and clearly strongly influenced by the wave dynamics of Chani and so on. But no matter what, you can see the perturbation energy just died at the location of the 0 line. So that wasn't explained. And by the way, I fell into the trap too. So the interesting thing is that when you do look at the observations and you start talking about zonal symmetry, and then you look at the zonal wind along the equator, here in height and here, and what you find, the reds are westerlies. This is not a zonally symmetric flow. And so what is this called? What is the reason for this? Is the complex structure a result of extratropical interaction, or is it a permanent feature? We'll come back to that. So I just was studying with Arkin, Arkin a few years ago. And what we did was we took Murakami and Unaya's idea of plotting the wind speed here in easterlies and then plotting perturbation kinetic energy. And what you find, of course, is that where you have westerlies, you have very strong perturbation kinetic energy. And so in other words, the strong observation hints of Rossby wave dynamics through this westerly duct. And then Jim Holton and I thought, well, we can do a little better than that. What we'll do is model a westerly duct, either weak or strong, and then we'll put forcing functions in. You can see the westerlies here, easterlies, and if you put a source in the right place, you get some propagation. You put it the wrong place, no, you get reflection and absorption. Or with a strong westerly duct, you get propagation through. So no explanation in where the westerly duct came from, but at least it was a place where one would expect to find extratropic Rossby waves. Just let me say that what we've done so far isn't working really, but so we thought we'd try looking a little bit at potential vorticity in isotropic coordinate system. And this was my former student, Bob Thomas, now in NCAR. And what he did was something very interesting. He looked at two surfaces, 345K up in the atmosphere, 315K lower. You see these two surfaces here in pressure versus electric. And then what he looked at were light correlations on the 345 surface relative to a major disturbance. And what you find is that you do indeed get all types of flow through this region. Whereas when you look at 315, so all of a sudden we have a differential response in the vertical for essentially the same forcing. So what Bob did was he looked at the, you're going to kill me for this chart, but here is X and Y. And so we're going to look at the isentropic structure along here. And this is for the mean December, January, February IPV. And look, by the way, this is the perturbation potential velocity. See how it's so strong in the region of the western duct. But you go down below to 315, whoop, there's nothing at all. It's all very strange. Well, let's look at the cross sections. Remember, this is X, that's Y. So here is the northwest, and here is the southeast. I said you'd hate me. And when you look at that, now this is the zone of you do the correlations from. It's our base point. And this is the background potential vorticity and the zonal wind. And here's what you find. It's something really remarkable. This is 3 days, 0 days, plus 3 days relative to this forcing. This is observations, by the way. And what you see, you can see A, B, and C, and you can see them moving along, but they're following the isentropes. And they're not projecting into the surface. This is real, Herbert real, not real. And so, in other words, you're getting a ducting along the isentropes of all these things. So this is a very, very interesting result, which will become important in a minute. So I'm going to give you, what we found is incursion of Rossby waves into the tropics. So I'm going to try and become a little bit more holistic and talk about where they come from and what they might do. So we go back, looking at these waves here, and we're looking at certain sectors to see where they are and what they do. So one is going to be the Asian monsoon region. And you can see this is the potential vorticity through here. And this is during our winter time. And so we'll see what we find. So now when we look on this is 370 climatology, and we get easterly jets, western ducts, jet streams, small jet stream here, which turns out to be very important, easterly jet, and so on. And so most of the features you recognize from an isomeric chart are here. So let's now ask the question what they look like. Oh, this is what I want you to do in this movie I'm about to show you. First, we'll do this region here and then this region here. So concentrate on that. So this is now July, and what we're seeing are breaking Rossby waves up here and filaments of potential vorticity going all the way to India, and they're going around the great anticyclonic gyre of the monsoon. And here we have Rossby waves moving along, and then breaking, and filaments moving down into the tropics. This is very exciting in a sense, because I'm not quite sure if these have been mentioned too much before, but what we're going to show is that to understand Indian rainfall, you have to understand these breaking waves. And then you have to understand where these breaking waves come from. So I always thought that these, I always thought that these did look like, oh dear me. Sorry about that. Okay. Sorry, bring it up again. Here we are. So I'm going to skip to the next slide and show you the impact of these guys. Okay, so this is the perturbation potential vorticity. It looks somewhat of a mess. These are the elements, the filaments coming down from the breaking waves. And when you look at the time series of potential vorticity in the 10 to 30 day band over South Asia, you get these bumps, and bumps, which turn out to be associated with precipitation. This is Sebastian Ortega and Violeta Toma, who did most of the work in this. So here we're looking at 10 days before precipitation was here. And what we're going to see are geopotential, green, negative anomalies, pink. And we're going to see now, this is the manifestation of those elements moving down over India and now dry. So we'll see that again very quickly. So the point is, it's one thing to talk about abstract potential vorticity elements, but when you're put in our normal meteorological jargon, they turn out to be highs, lows, and maximum precipitation. And the reason I bring this up is principally because to understand Indian rainfall, you can't just look at India. You have to look broader, or not just India, anywhere. So now let's look at the boreal winter. This is now February. And what you're going to see are these waves moving off here and the breaking through here. And notice, by the way, the blue ones, it's just the opposite. Look at this here, moving out of the subtropics in the southern hemisphere. We'll come back to that in a little while. Ah, there's the breaking wave here. Darren Moore and his colleague Natsu have done a lot of work on this. So anyhow, as I had to say, if you think these are ink blots, you have to tell me what you think you see. Big NCAR-wide psychological examination. So snapshots, these are from Natsu and Moore, a lovely paper. And you can see what I've done is color in the anomalies. And as you move through here, so you'll see, now here we go. These are the breaking waves. And this is interesting because you then have to ask the question of why are they breaking? And also, to be fair to Giuliani, I sort of dismissed his idea of zonal symmetry. But I wonder, in a sense, if you can wonder if he was also thinking of something like this. It's interesting there. So, summary so far. In both the summer and winter, in both hemispheres, westerly ducts appear downstream of westerly jets. And it turns out that westerly ducts are conduits of Rossby waves, first moving eastward into the westerly duct, breaking and transporting PV equatorward. So, what's the source of the Rossby waves? What dictates the location of the breaking waves? Is there a mechanism for the return of PV poleward? Why should we even bother about that? Aha. And we now consider a simple theory leading to a governing constraint. So what we're going to do, and I don't want to labor this, but I can give you 100 papers to read if you would like. So this is potential vorticity. We define it on an isotrope, and it's conserved in adiabatic frictionless flow. But we want a quantity that is conserved when there is dissipation and heating. And Haynes and McIntyre developed this potential vorticity substance, which is given by the potential vorticity times the isotropic max density. But if you're interested, I can spend more time on that. But so what it says is that if you look at two surfaces, potential surfaces, 3 to 132, and by the way, these P's just refer to which way pressure goes. And here you have the perturbation, the potential vorticity contours. It says that if you have a velocity v, which has a component v dot n, in other words, towards the equator or across a potential line, latitude line, you can define the advection of potential vorticity flux. If you do that, what you can do, you can derive a conservation potential vorticity equation, blah, 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 and you get to this interesting thing, which is what is referred to as the impermeability theorem. And I'll tell you why it's why impermeability in just a minute. And by the way, the total flux of potential vorticity substance is effective heating and friction. That's very important, or greatly underutilized right now. So this is my old friend Michael McIntyre and Haynes. And so the theorem says that there are no sources of sinks of PV between the isotopes that don't intercept the ground. And PV fluxes cannot occur across isotopes. Do you remember that diagram of the advecting waves moving through the isotopes? They were staying beautifully centered on those isotopes. So if you then integrate across the latitude circle, then even in the presence of heat and dissipation, it says that the zonally average quantity here, which is the potential vorticity substance, equals 0. So at the end of it all, the isentropic potential vorticity substance flux across the latitude line is 0. So McIntyre described the polar vortex as a wave turbulence jigsaw puzzle. And there are regions of strong PV gradients where oscillating modes dominate, waves on jet streams, regions where Rossby waves break. And so we've tried to sort out McIntyre's jigsaw puzzle a little bit hopefully going from here to here and not from here to here. So let's see. So what you find is that the Rossby waves breaking, leading to equatorial advectional PV fluxes, and also divergent circulations like the monsoons, local Hadley circulations. And we push the question, are these regimes related? So to give you an idea what these look like, this is January, and it's the snapshot here from January 19th, 2001. This is the climatology, so you'll see that these are wave breaking up here. And when you look at the mean flux across 30 degrees north, and so that's here, what you find is strong poleward flux, strong equator flux, minus 3,600, minus, so then plus 3,800. And they average out roughly to zero. So in other words, this is the impermeability theorem showing you that if you have a flux to the north, you have to have a flux to the south side. This is a pretty good constraint. This is the summertime, 9th of July, and you can see that in a, here's our, this is one day, this is a climatology, and you see these breaking waves moving through here. So the mean now across 30 degrees north is almost adds up to zero, and 10 degrees north, not so well, but pretty close. So we have these waves, we'll call them recursive waves in the sense that they're breaking all the time. And they're breaking in a very specific region. They're breaking in the westerly duct region, which in a sense you might ask, well, do the Rossby waves themselves form the westerly duct? Or do they just go into this climatological feature? We'll see. So let's consider two ideal situations. A zonally symmetric model is having held and ho, and there's only asymmetric model. And that would be where you would have symmetric circulation, Hadley circulation, 200 millibars, for example, flow away from the equator, flow away from the equator. That should be 2m, by the way. I apologize for that. So the zonally symmetric circulation, where V is greater than zero everywhere, like in Hadley circulation, the PV flux equals zero everywhere. Remember the formula that V times the potential vorticity times the density equals zero average around electric circle. So the only way that this can occur is if the PV flux everywhere is zero. On the other hand, if you have an asymmetric circulation, now, again, that should be 2m. You get flow away and flow towards, but now, in order to honor the impermeability theorem, oh, by the way, this honors the impermeability theorem too. There's no potential vorticity flux anywhere. Here you must have, here you have poleward, and here you must have a return flow. So this is a nice binding thing. Return flux must compensate for the poleward flux. So consider a system with no heating. And now let's add some heating here. And what you find is, just going back one, these are isotopes. And so what you find is that a concentration, here's the heat source, flux away, and there must be a flux down here. And what you find is that, in more detail, the westerly maximum is created by the heat source of forward PV flux here. That is unstable, it forms waves. The waves move into here, and where they break and send their PV down towards the equator. Interesting thing is this is divergent dynamics, like a big sea breeze. This here is Rossby dynamics. So you have a combination of Rossby and divergent dynamics. This is largely the work of Sebastian Ortega. So breaking waves are important, but why do they break? This is a little simulation of breaking waves. So pretty, see, this is a source here, and 1 day, 2 days, 3, 5 days later, and you can see these elements breaking off. So the question is, why do this irreversible distortion occur downstream of the Wesley chain? So we did a lot of work a long time ago looking at what happens to waves propagating into variations of the flow. So this, here we have udx is negative, and so on. And what you find is that following Bretherton years ago, Bretherton and Garrett, if the frequency is held constant, these waves will squash up. And indeed they do. And what they do, they break when they are so distorted they can't conserve potential vorticity, and they break. So these are important things. This is an aside for you. The similar principles can be used to account for the great cloud bands of the Southern Hemisphere. Here's the great cloud band. This is the convection associated with it. What we have in looking at you have a jet stream here. You have waves coming off. They encounter this negative stretching deformation and they break. And what you find that all this breaking takes place in the, this becomes the region where the Southern Hemisphere has an equatorial component of potential vortices. So this was work done by Matt Molansky a number of years ago. He's now University of Hawaii. So some of the peculiar features that we've been talking about become rather explainable. Just give me one more minute. So hemispheric balanced communication. So here what we have, some type of heating here, and there's a poleward advection of potential vorticity. We get a building of the gradients through here, jet stream, and waves form on here. They propagate into this distortion, breaking, recursive region, which has this dudx less than 0. And they get the waves propagating down towards the equator and sometimes become part of the divergent circulation here. So you have a combination of a dynamic circulation producing the Rossby waves and the Rossby waves returning the favor, putting the potential vorticity back towards the equator and then feeding back into this. So it's sort of rather nice in a sense. So a quick summary, the isotropes will be concentrated by divergence and PVS substance will be continually transformed poleward. And I think the important thing here is that in all circumstances, we see recursively breaking Rossby waves. So we had this combination of Rossby dynamics and divergent dynamics. And if you look at the global balance, this is not the best diagram, but it'll give you an idea. Have some heating at the equator, and you'll form, and this is maybe spring or autumn, and you form a jet stream here, breaking waves, propagation towards the equator. So one can start to think about in this global sense now, what about if I were to move this north or move it south? What happens to the transport of potential vorticity towards the equator? What happens if I were to introduce all of a sudden some type of perturbation into the forcing functions? Who knows what, but let's assume a warm body of water somewhere alters the divergent circulations. What we say, because of the impermeability theorem, that there's going to be some response to the Rossby field too. And therefore, we have tied in interhemispherically things. So anyhow, the impermeability theorem places severe restrictions on planet-scale motions. The conservation potential vorticity is exact and allows both diabatic and dissipated processes. This is very strong. It's probably not too well understood or utilized, especially by us, to a full extent. And this is my IMO, which is, in my opinion, and this is work in progress. So it allows us to think of some of the geophysical problems that we looked at before. One is the radiative and precipitation mirroring. These are the more difficult problems to explain in terms of impermeability. So it's probably a required overall balance of the annual climate. You can think about that in terms of that global picture I showed you a minute ago. Precipitation is a bit more difficult given the complexity of distributions and processes, but somehow there's an overall constraint by perhaps the impermeability theorem. So anyhow, we have to wait and see. Martian global dust, very quickly. This is, what's his name? Martian, heading off to a bit of trouble. Mars is interesting, it's a very simple system, has very complex and very large topography, and strong elevated diurnal heat sources. Latent heating not important. Regional perturbation of energy balance may cause dynamic imbalance, thus interhemispheric balances, and then the impermeability theorem sets in, and you must have an adjustment until a new equilibrium is reached. And so who knows if this makes any sense at all. The ice age timing, changes in distribution of top of atmosphere, radiation, with all orbital oscillations requires dynamic adjustment for a new equilibrium. These changes occur with the impermeability theorem in mind, but that's a very difficult thing to push. So I didn't list any references, but if anybody would like them, I'd be happy to. Thank you very much.
Excellent. Thank you, Peter, for a great talk. And I'll remind people that there are a couple of ways you can ask questions. You can either raise your hand and I'll call on you. And also feel free to put some questions in the chat if you prefer to have me read them. So I'll start off. We have a question from Christopher Cruz, who asks, is there a time scale below which net meridional PV substance flux may temporarily be non-zero around the latitude circle? So it's pretty sure the impermeability theorem says no.
That's a good question, a very, very good question. I'm not quite sure I know the answer. But it's probably a very important thing to find out. We know in the mean, it works out very, very well. And you can look at the transients and you can see them doing their thing, sort of nicely adding up to zero. But on the time scales that you do have, absolute zero, I don't know, but that's one thing that we can do with our WIP, work in progress.
All right, thank you. Well, while we're waiting for another question, I guess, a question I had was wondering if you could speak a little bit about the timescales at which the impermeability theorem might, play a leading role in achieving any kind of interhemispheric synchronicity. I know you discussed a wide range of timescales for possible applications, but is this, acting on days, weeks?
The answer to the first question and also yours, we know it works in the relatively short mean. I didn't show you, but give me a minute, I can go back. I've lost life here. Oops. Are you still there, people?
We're still here.
Not quite sure I am. No, here we are. Just 1 second here. That's a very good question. I truly appreciate that. And here we go. So I've only got the mean fluxes across. Well, I don't have the fluxes, for example, on the 19th of January. But thank you very much for that question. That's something we can do very, very easily. It doesn't help me answer the question, but I think you'd find that Well, I don't know. It's a good question. Thank you. Yeah.
All right. I see a question from Adam. Adam, you can go ahead and unmute yourself.
Yeah. So I'm reaching back to some stuff I looked at a long time ago, but the moisture budget for the subtropics has a extratropical recirculation term, which, if not for that term, the subtropics would be much drier than they're observed. And so it occurs to me that, is this not the means in which moisture is recirculated back into the subtropics through these ducts?
That might be a nice clue about the precipitation aspect. Yeah, that's good. When you say you're looking back to work done or thought about earlier on, not as long as I have.
When I was a PhD student, I was doing moisture budgets of CAM.
Yeah.
And I think it was Oliver Paul Lewis co-authored paper on the moisture budget of subtropics and isentropic coordinates, and that was a big term, but it was just had never heard of extratropical recirculation before.
Could you send that to me? I'd really appreciate it.
Absolutely.
Yeah. I think that the thing I like about whatever we've done is it makes you realize that most of the stuff we've done in the past isn't very good. It was limited. It's one thing for Jim Holton and I to fire salvies of Rossby waves at a hole in the Eastleys, but we didn't ask the question where the Western duct came from, and sort of rather a major omission.
All right, thank you. Still have a moment for an additional question if anyone has one. And not seeing any. Peter, I'd like to thank you again. And everyone, look forward to seeing you again next week.
Okay, thank you very much.